We're now going to look at a way of estimating values of a differential equation using what's known as the Euler Approximation Method. The basic idea is we're going to use a bunch of line segments to make a piecewise linear approximation of the solution to the differential equation. So if we can't solve the differential equation, it does give us a pretty good approximation of the solution. So in order to do this, we're going to look at a very basic differential equation. We're going to consider the differential equation dy dx equal to y, where we know it passes through the point y of 0 equal to 1. And we want to try to find the approximate solution when x is equal to 1. So essentially y of 1 is equal to what? So how do we go about doing this? Well, we're going to start with the point that we know. x0 is 0 and y0 is 1. And the idea is I want to slowly increment x to get it up to 1. I don't want to jump straight to x equal to 1. I want to take it in little pieces. The smaller I increment up, the better of an approximation it's going to be. We're going to increment up by 0.25, so by 1/4. In this case, we would have x1 is 0.25, x2 is 0.5, x3 is 0.75, and x4 is 1. And so now we want to find an approximate value for y for each of these numbers. And how we're going to do this is we want to find a little line segment between our initial point x0, y0 and the point x1, y1, where y1 is going to be an approximation for y at the point x1. So we need to be able to find these slow approximations. And how we're going to do this is we're going to use this formula y1 equal to y0 plus h dy dx. The idea of this is we're drawing these little line segments between x0, y0, and x1, and this new value y1. We have the slope. The dy dx gives us the slope of that line. H is the increment, how much we've stepped up. And then y0 just tells us where we initially started. So in this case, y1 would be 1, the value of y0, plus h, 0.25 in this case, times dy dx. In this case, dy dx is y, and y0 is 1, so this is what we would use. It gives us 1.25. So we have the solution is approximately 1.25 whenever x1 is 0.25. For y2, we're now going to use the value for y1. So we start with the value for y1. We then need to add h, and we multiply by dy dx evaluated at y1. So once again, in this case, since our differential equation was just dy dx equal to y, we need to multiply by 1.25. Which is approximately 1.56. So now I have my value for y2. For y3, we're going to do the same thing, but this time we're going to use the value for y2. So for y3, we would have y2, 1.56, plus h, which is 0.25, times dy dx, which is just y, 1.56, which is approximately 1.95. And we can repeat that again, this time using y3 to get that y4 is equal to 2.44. So our approximate solution when x is equal to 1 is 2.44. We know that y is going to be approximately 2.44 when x is equal to 1. And while that did solve our problem, let's look at a visual of exactly what it is that we did. So here I have Desmos, and I've done a lot of work setting this up beforehand, but we start with these points on the x-axis. This is how I increment it up. I have 0, 0.25, 0.5, 0.75, and 1. So these are my just x values and the way I've incremented up. And we can see how we did that here. We just progressively took the previous point and added our h value, which was 0.25. For the y values, we essentially had the formula that yn plus 1 is equal to the previous value plus h, 0.25, times the derivative, which was just y. So we have all of the formulas here, and they go out to more decimals than I went out to whenever I did it, but we do see the values that y is supposed to be. We can then plot these values. So now I actually have points, x0, y0, x1, y1, x2, y2, x3, y3, and x4, y4. And essentially what we did is we connected each of these with line segments and essentially just put these little line segments between them to approximate the solution. And this is the idea of what it was that we were doing. Like I said, the smaller our increments are, the better of an approximation this will be. We can see that if we graph the actual solution, that we're not that far off. Clicking on this point, we can see that the actual value is 2.718. We got 2.44, so we actually are pretty close. And if we would have let h be something smaller, like 0.1, we would have been even closer. While that was a relatively simple differential equation, let's consider a slightly more complicated one. dy dx equal to x squared y. And while I won't actually solve this one or get an approximation, I do want to discuss how it's done. Determining the x values is always going to be the same. We figure out our value for h, our step size, and we add that value to the previous value for x. So we're given x0. To find x1, we do x0 plus h, x2 would be x1 plus h, x3 would be x2 plus h, etc. For y1, we would have y0, which we're given, plus h times dy dx evaluated at x0, y0. So in this case, that would mean y0 plus h times x0 squared times y0, since that's what the differential equation tells us, square x and multiply by y. For y2, we would have y1, the previous value for y, plus h times x1 squared y1. So we keep just using the previous point to find the next one.